Hi everyone, my name is Jahadad.
And my name is Taddy, and today we are going to be looking into the full hybridization of carbonate or CO3 to negative. So let's get into it. So we're going to start off by drawing the Lewis dot diagram for this carbonate ion. Before we start, we have to figure out whether this is an octet or a non-octet molecule. Let's check if it follows any of the conditions for it to be non-octet.
The three conditions consist of the following. 1. The central atom is either a halogen or a noble gas. 2. The number of surrounding atoms is greater than 4. Lastly, 3. The molecule is sulfur paired up with a halogen.
That's right. However, this is an octet molecule, as CO3 2 negative does not follow under any of these guidelines. First, we're going to start with the need-have method to find the number of electrons needed for the molecule to become stable, and the number of electrons we already have.
To start, carbon needs 8 electrons and oxygen also needs 8. There are 3 oxygens, therefore we take 3 oxygens and multiply by 8. As in 8 electrons per oxygen, this equals 24, and then we'll add the 8 electrons that carbon needs to reach a final need number of 32 electrons.
Then we're going to find our have number. To start, carbon is in the 14th column, meaning that it has 4 electrons to offer. Oxygen is in the 16th column, meaning it has 6 electrons to offer. Same process as before, we're going to take our 6 electrons, multiply by 3, representing the 3 oxygens we have, and then add on the extra 4 electrons that carbon has to offer. However, our molecule has a charge of -2, meaning that 2 electrons are added on top of that. Therefore, instead of 22 electrons, we're going to end up with 24 electrons for our have number.
Next, we have to look at the number of bonds we have in our molecule. To calculate the number of bonds, the general formula is our need number, subtract our have number, divided by 2. In this case, we'll end up with 32 minus 24 divided by 2, which comes out to a total of 4 bonds.
Great! Now let's get to drawing. First, let's start off by drawing our central atom, which in this case is carbon. Then we're going to draw our surrounding atoms, our oxygens. Since we have 3 oxygens, we're going to place them in a triangle formation around the central atom.
Now let's place our bonds. We have 4 bonds, but 3 surrounding atoms. So this means that one of the surrounding atoms will get a double bond. It doesn't matter which one, so we'll just place it in one of them and move on. Now that's done, we just subtract the number of electrons we just used from our have number. Originally we had 24 electrons, but we just used 8 since each bond uses 2 electrons.
This means that we're left with 16 electrons. Now, we have to fill the surrounding atoms with electrons before we move on to do anything else. We'll place 6 electrons each on the first 2 and 4 on the last to ensure they are fully satisfied.
As there are no more extra electrons, this means we won't have any lone pairs on our central atom.
You're right, Jahadad. If we have any extra, we'll place them on our central atom, and it would change the shape of our molecule. But I'm getting ahead of myself. Let's focus on the next step, and we'll cover the geometry and shape later.
Great, we're on to the final step of our Lewis dot. We're missing one crucial part from our drawing. This is a polyatomic ion, we need to indicate that it has a charge. In order for us to do this, we will draw in 2 square brackets around the diagram and label the charge on the top right corner, which in this case is a 2-. Finally, we can move on to the separ. Let's talk about the bonding pairs.
We have 2 single bonds and 1 double bond, equaling 3 bonding pairs in total. Let's circle them in blue. Now, since we have 3 bonding pairs, this means we have 3 electron groups. Therefore, this molecule falls into the 3rd category. If we have a quick look at our reference sheet over here, we can tell that the geometry of this molecule will be trigonal planar.
Now, let's draw the 2D diagram on the side of this molecule. In the cases of electron group 4 and 5, we would draw a 3D diagram. However, this molecule is 2D because the geometry is trigonal planar. Don't forget to add the square brackets here as well to indicate the charge on the ion. Let's have a look at this diagram. As there is no lone pairs, the name of the shape will be the same as the geometry. Trigonal planar. Finally, let's draw in our angle with a red pen. We know our angle is 120 degrees, So right here, we'll draw it in with an arrow and write out 120 degrees. This marks the end of our complete VSEPR diagram.
Now, we're going to find the condensed electron configuration for our central atom, which is carbon. To write it out, we're going to first find carbon on our periodic table and look at the noble gas that comes before it. In our case, the noble gas beforehand is helium. Then we start there and work our way towards carbon, making sure to properly name each step we take.
First, we go through the second row, so we have to write a 2 to show that the energy level we're starting in, with the S block. Each block represents an orbital. The orbitals go in order of S, P, D, F. We pass through two elements in the S orbital before reaching the P orbital. And we can show this by adding an exponent of 2 above the S. Then there are 2 elements, including carbon, that we need to pass through in order to reach carbon. So we're going to indicate this by adding an exponent of 2 above our P. However, let's not forget our compound has a charge of 2 that needs to be accounted for. So we're going to add it in right on our last orbital and change the exponent 2 on our P orbital to a 4. That is our complete condensed electron configuration for our central atom.
Now we're halfway done. Let's get to our energy level diagram. First, we're going to start by drawing the X and Y axis. The Y-axis will represent the potential energy, or EP. The X-axis represents the types of orbitals. We're going to draw in our S orbital first and draw a dotted line spaced out just enough that we have room to write in our S orbital, but that we also have room for our P orbital. The P orbital should have a bigger space than the S orbital because it has 3 orbitals and can hold 6 electrons, while the S only has 1 orbital and therefore can only hold 2 electrons.
To start us off, let's write helium in as our noble gas, right on the bottom of our S section. Then right above, we're going to draw in 1 underscore to represent the orbital and name it accordingly. So in this case, it would be 2s.
Then in the P section, we draw 3 underscores in a row a little higher than the dashed line in the S section, as S orbitals have more energy than P orbitals, and label the orbital 2p. Now we can finally start placing in our electrons. However, there's a certain order that we have to place them. According to Hund's rule, single electrons must be placed first, before pairing up with other electrons.
So we'll start by placing in our electrons in the S orbital. Based on our condensed electron configuration, there are 2 electrons in this section, so let's draw them in. For our P orbital, we have 4 electrons, so let's start by placing the single electrons first, and then we'll place the 4th electron in the first orbital. However, the 4th electron will be drawn facing down instead of going up.
Now that we've finished our energy level diagram, it's time to hybridize our molecule. So we're going to draw an arrow and write hybridization. Now let's draw the base diagram again. The next step is to write out our different types of bonds based on our Lewis dot.
First, let's have a look at our single bonds. Single bonds can either be sigma bonds, represented by a sigma symbol, or coordinate covalent bonds, represented by CCB.
Generally, we would naturally look at these bonds and think sigma bond because those are the most common. However, we need to take a closer look at the number of electrons each surrounding atom has to offer. Oxygen only has 6 electrons to offer. However, each one is stable because carbon is providing both of the final 2 electrons. Since the 2 electrons in the bond are both coming from the central atom, these bonds aren't sigma bonds, but they are coordinate covalent bonds.
Now let's take a look at our double bond right here. With double bonds, the first bond will be a sigma bond, and the second one will be a pi bond. So let's write out all our bonds in order. The sigma bond is first on the list, followed by the 2 coordinate covalent bonds, and the pi bond is last. However, the pi bond is a special case. Pi bonds are never included in hybridization, so we add it in the very end of our diagram. For now, let's draw a little star next to it on the list to remind us that it won't be included.
Now let's draw in our hybridized orbitals. Hybrid orbitals must all come from the same energy level, so in this case, energy level 2. We're going to draw 3 dashed lines right in between the S and P orbitals on our energy level diagram. All hybridized orbitals go in between the two highest orbitals. For placing electrons, we start off with the sigma bond. Sigma bonds have one electron, so we'll only draw one electron in the first orbital. Coordinate covalent bonds have 2 electrons each, so we'll fill in the last 2 orbitals with 2 electrons each.
Now let's do some rough work to name our hybridized orbitals. We have 3 hybridized orbitals, and therefore we can check off the 1s orbital and 2 of the p orbitals. Our hybridized name will be the energy level number 2, s with 1 as the exponent, and and p with 2 as the exponent, since we checked off 2 of the p orbitals here. If we had checked off all 3, p would have an exponent of 3. Our final name written underneath the dashed lines on the diagram would be 2sp to the power of 2. That is our full hybridization of CO3 negative 2.
Now let's take a look at the intramolecular and intermolecular forces for this carbonate. Intramolecular forces are the forces of electrostatic attraction within a molecule. These are the forces that hold up the molecule together. They occur between the nuclei of the atoms and their electrons making up the molecule, i.e., covalent bonds. Intramolecular forces help determine the chemical properties of a substance. We'll start with the polarity between bonds using the electronegativity, otherwise known as the En values on the periodic table provided. After that, we'll look at how the shape of the molecule, based on the Weissenberg theory, allows us to determine if the entire molecule is polar or nonpolar.
The En of carbon is 2.5, and the En of oxygen is 3.5. Therefore, the total electronegativity is 0.5, meaning that the bonds between the carbon and oxygen atom are polar. The polarity results from an unequal sharing of valence electrons. In carbonate, the shape is symmetrical and there is no net difference in charges. This means that the compound is a non-polar ion. While the carbonate ion is nonpolar with regards to its molecular geometry and equal distribution of electrons, it does have an overall charge of 2-. This overall charge allows it to interact with polar molecules like water.
Now to take a look at the intermolecular forces. Intermolecular forces are the forces of attraction between 2 molecules. Examples are London dispersion forces, dipole-dipole interactions, or hydrogen bonds. These forces are much weaker than intramolecular forces and are much easier to break. Physical changes, for example, changes of state, break or weaken these forces, and new substances are not formed when broken. Lastly, these forces also determine the physical properties of a substance.
For example, H2 is a molecule that has 3 forces. Hydrogen bonds, dipole-dipole forces, and London dispersion forces all exist in water. Since these forces are so strong, water has a higher melting point than most small molecules. It has a melting point of 0 degrees, which is already much higher than most. Majority of molecules of similar mass are gases at 0 degrees. However, because of its such strong intermolecular forces, water also has an extremely high boiling point of 100 degrees Celsius. This is because it takes more energy to break apart the hydrogen bonds.
CO3 only has London dispersion forces. As it's a non-polar molecule, it can't have dipole-dipole forces, and there's no hydrogen bonds, so the only acceptable option would have to be London dispersion forces. Since LDFs is the weakest force, carbonate is a gas at room temperature, and therefore it has an extremely low melting point. Alright guys, so that was our full hybridization for carbonates.
Thank you guys for watching, and
we'll see you next time.